right, in this set of notes, we're looking at perpendicular bisectors of chords. In this case, we've already talked about what it means for a segment to be a chord. Remember, a chord is a segment that joins 2 points on the circle. So here I see a chord from P to Q. I see another chord from R to S. And then likewise some segments here that are chords. So we have 2 theorems that we're looking at today related to chords in a circle. The first, if the diameter of a circle is perpendicular to a chord, and in this case we can see the diameter of the circle RS, we know it's a diameter because it passes through the center, is perpendicular to the chord PQ. So if the diameter is perpendicular to a chord, then the diameter bisects the chord and its arc. So in this case, what that's saying, if the diameter, segment RS, is perpendicular to a chord PQ, then 2 things happen. The diameter bisects the chord, which means segment PT is congruent to segment TQ, bisects the chord, cuts it into 2 congruent parts, and it bisects its arc. And remember, the arc for segment or chord PQ would be the arc PQ. So that's going to be bisected, which means, and arc PR will be congruent to arc RQ. The same could be true for arc PS and arc SQ. So if you bisect, or if we have a perpendicular chord and diameter, then it bisects the chord and bisects the arc. All right, the second theorem, if one chord is a perpendicular bisector of another. Now remember what perpendicular bisector means. So these 2 chords have to be perpendicular to one another, and one of them is being split into 2 congruent parts. So if one chord is a perpendicular bisector of another chord, so here chord AC is a perpendicular bisector of chord BD, then the first chord is a diameter. So segment AC in this case must be a diameter. So in terms of what that would look like in a problem, if segment AC is perpendicular to segment BD, so I have to know they're perpendicular, I have to know there's a right angle, and that and is important, one of them is being bisected. So here segment BE is congruent to segment ED. If they are perpendicular and one is being bisected, then the one that's doing the bisecting, in this case segment AC, is a diameter. So we have 2 things that we have to be given, or we have to be able to know are true. We have to know that there's a right angle present, and we have to know that the segment's being bisected in order to conclude that it's a diameter. Okay, so we have 2 examples then that we want to look at related to these 2 theorems that we were just talking about. And with that in mind, there is something on the diagram that I forgot to give us that needs to be there. So in this case, you need to be given that segment AB is perpendicular to segment GE. All right, so with that in mind, there's a right angle right here. All right. Now, let's determine what we have. Given that the length of segment AB is 12, so from A to B is 12, and DE is 12, DE, there again, is 12, and CE is 7. Now, CE is our radius, so that might be helpful. Find the length of segment CG. So what we're trying to determine in this case, let's call this X for a minute. That's what we're trying to determine. All right, so with that in mind, we look at our first theorem at the top of the page. If a diameter, and if I extend this segment from E through C all the way up, if a diameter is perpendicular to a chord, perpendicular to AB. Then it bisects the chord, which means these two portions, AG and GB, are congruent segments. Now, with that in mind, we know AB was 12, so each of these would have a length of 6 units. Okay, so how does that help us determine anything? Well, we also know, in this case, that the radius is 7. So if the radius is 7, then that indicates the length from C to A, that radius would also be 7. Remember, the radii in a circle are the same length. So at this point, I can see a right triangle whose sides are x, 6, and 7 units long, which tells me the Pythagorean theorem is useful in determining the value of x. So x squared plus 6 squared equals 7 squared. So square our values. We get 36 and 49. Subtract 36 from both sides to get 13. Take the square root of both sides to get x equals the square root of 13. Now in this case, we're not given any indication as to what type of answer we want, whether it's to be exact or whether it's to be rounded. When that happens, assume that you want to leave it exact. And in this case, we get x equals the square root of 13. If a problem had asked for the decimal version, then I'd go to my calculator and type that in and determine what that decimal value would be. All right, so at this point, I would suggest that you pause the video and give number 2 a try, and then we'll come back to that in just a moment. All right, so assuming you've looked at number 2 then, given that the length of segment AD is 40, and looking at the diagram, I can see that that's cut into 2 congruent parts, so each of these will be 20 units long. And the length of segment CD is 25. Find the length of segment CG. Now, CG in this case is, I'm going to call that X. We've had a theorem previously that said if 2 chords were congruent, then they are equidistant from the center. And here, all 4 of these parts were marked as congruent. So these were each 20, which means these parts over here are also 20, which means this length from C to G and this length from C to F must be the same. They must both have the same length. Now remember, we also said at that time that the distance from the center to the chord makes a right angle. So here again, we've got some perpendicular segments and we've got a right triangle we can work out with. So using that right triangle, x squared plus 20 squared equals 25 squared. Squaring our values, we had x squared plus 400 equals 625. Subtract 400 from both sides and take the square root of both sides to get x equals 15. And those are the 2 theorems then that are related to chords and perpendicular chords specifically.